So we'll get started with today's discussion. So I'm going to be talking from this particular paper, which is actually a review paper. So that's the name of the paper, Foundations of Control and Estimation over Lossy Networks. I think this is from maybe 2007, I think. So this paper basically reviewed a large amount of literature that was available at that point of time, which talked about what happens, how do you control a system and how do you estimate if the packets are getting dropped, if the control packets or the communication, the sensor packets are getting dropped. So typically when you have an attack on the system, that's what the attacker is trying to do. So that's something we'll be talking about over the next few classes. So the first topic that I want to talk about is control over lossy network. The next topic will be estimation over lossy network, and then we will talk about joint control and estimation over lossy network, and we'll enforce the separation principle for that particular problem. Okay, so if you recall, this is what the problem statement was. So this is what we were trying to study in the previous class. Let me change the notation slightly because it becomes easier to understand because that's what we are using in the assignment as well. So I guess, okay, let me use alpha t because I'm using gamma t already for something else. This is full state observation, so yt equals to xt. I want to minimize summation xt transpose qxt plus alpha t times ut transpose rut. T goes from 0 to capital T plus xt plus 1 transpose qt plus 1 xt plus 1. As usual, wt is mean 0 covariance sigma w, and alpha t is Bernoulli alpha bar. So alpha t, and this is IID, and this is IID. I want to minimize over all gamma t that maps xt to ut. We are also going to assume that this is TCP-like architecture, TCP-like, which means alpha t is known. No, I should be a bit precise. After ut is transmitted, alpha t belongs to 0, 1 and is observed by the controller. I need to put an expectation here. That is my problem statement. Now we have studied dynamic programming, so we'll just apply dynamic programming on this particular problem. But there is a twist, so after you note it down, we'll talk about what that twist is. So the question for you guys is, what does controller know at time t? Before it transmits the information ut, what exactly are the variables that the controller has seen until that point of time? So naturally, controller has seen x1 all the way to xt. Controller has seen u1 all the way up to ut minus 1. Let me write it down. Information of the controller at time t. It's x1 to t, it's u1 to t minus 1. What else does the controller know? Anything else that the controller knows at time t? It turns out that it also knows alpha 1 to t minus 1. It knows the sequence of packet drops until now because it's a TCP-like protocol. It's a TCP-like protocol, so the controller gets the acknowledgement whether the packet was successfully transmitted or not. And so this variable alpha 1 to t minus 1 is also observed by the controller. Okay. Perfect. What does controller know about the packet drop probability alpha t? So controller also knows that alpha t is going to be 1 with probability alpha bar and 0 with probability 1 minus alpha bar. Okay, and this alpha t is independent of everything. So independent of this, independent of this, independent of this. Any questions? Perfect. So let's try to solve it. We are going to apply dynamic programming algorithm. We studied dynamic programming back in lecture 10 or 11 or something like that. So we'll just continue to work on, continue to pick up this particular problem from where we left at that time. So anyone remembers what we do in dynamic programming? We first look at the terminal cost, and then we move backward. We look at cost at time t minus 1, optimize that, then look at cost t minus 2, optimize that, and so on. So we'll apply dynamic programming onto this particular problem and try to solve this problem. Okay, so what is the cost to go at time capital T? I want to minimize my policy gamma T of xt should be argmin of ut So the cost to go is xt transpose qxt plus alpha t ut transpose rut plus xt plus 1 transpose qt plus 1 xt plus 1. This is my cost to go. Oh, I need to put an expectation, because there are some things that the controller doesn't know. Controller doesn't know alpha t and the controller doesn't know wt. So that's why I need to take an expectation. What should we do now? We need to collect all the terms that contains ut together. So xt is known to the controller, so this one doesn't participate in the expectation. This part is the thing that the controller decides, but alpha t is something that the controller doesn't know. And then xt plus 1, this is equal to axt plus alpha t but plus wt. So there are, again, alpha t and wt are things that the controller doesn't know, but at the same time it is independent of everything that we have seen so far. Remember, these two are IID random variables or random vectors, so these are all independent. These two terms are independent of whatever I have seen in the past. So let's try to take the expectation and see what kind of results we get. Okay, any questions so far on this? No? So this is how we apply dynamic programming. So this is for the first time we are doing this dynamic programming in the stochastic setting. We did talk about dynamic programming in the deterministic setting back in lecture 10 and 11. So this is how you would do it in a stochastic setting, where you take the expectation, but there are some variables that the controller already knows, and the other variables that the controller doesn't know, you take the expectation with respect to those variables. So let's try to collect all the terms together. So I have xt transpose qt x qxt what is the expected value of alpha t? Can someone tell me what the expected value of alpha t is? Alpha t is Bernoulli alpha bar. Yeah, so it's 1 with probability alpha bar and 0 with probability 1 minus alpha bar. So what's the expected value? It's 1 times alpha bar plus 0 times 1 minus alpha bar. So it's equal to alpha bar. UT transpose RUT plus. Now I have this term xt plus 1 transpose qt plus 1 xt plus 1. So I need to expand it. So let me expand it a little bit. I have xt transpose A transpose qt plus 1A xt plus alpha t square. I need to take the expected value here. Square there should be a 2 here. Okay. Which of the terms are cancelling out? Are there any terms that are not participating in the optimization? Remember, I have to minimize with respect to UT. Yeah, I think these are all the terms we have. We don't have any additional terms. Okay, so which terms are going to cancel out? So let's look at it. Expected value of WT is equal to 0. So I see an expected value of WT transpose. So this term will go to 0. It wouldn't participate in the optimization. Okay, what else? This term is just a constant because WT transpose QT plus 1 WT, this is just a constant which depends on sigma W. So this term also doesn't participate. It's just a constant that gets added, but it doesn't really participate in this minimization because this is a constant. So what are the terms that depends only on u? There is this term that depends on u. There is this term that depends on u. And then there is this term that depends on u. All the other terms are independent of u. It doesn't participate in the optimization at all. So this is independent of u. It's just xt transpose some matrix xt. This is xt transpose some matrix xt. This is constant. This is equal to 0. Okay. So as much as this expression looks pretty bad, it's actually not that bad once you think about it. What is the expected value of alpha t? We already said that this is equal to alpha bar. What about expected value of alpha t square? What is that equal to? What is expected value of alpha t square equal to? Can you check? So alpha t square, what is alpha t square? This is 1 with probability alpha bar, or rather 1 square, and then it's 0 square with probability 1 minus alpha bar. So what is the expected value of alpha t? It's 1 square multiplied by alpha bar plus 0 square multiplied by 1 minus alpha bar. So this is actually also equal to alpha bar. Okay, so our life is even better. We have an alpha bar here, and alpha bar here. So in all these three terms, we have a constant alpha bar that is getting multiplied. One more thing that I forgot to mention, whenever we are solving the LQR problem, the Q matrix and R matrix are all positive, definite / semi-definite. So Q is positive semi-definite, Qt plus 1 is positive semi-definite, and R is positive definite. Okay, so this is an underlying assumption in any LQR problem. You know, the funny thing is, I was teaching exactly the same equation in my optimization class today. So I didn't have to prepare. I had to prepare once, but I could prepare for both classes together. That's great. Okay. The only thing in optimization classes, there was no alpha bar, there was no packet drop there. And there was no uncertainty, there was no WT there. But everything else remains the same. Okay, so how do I solve this particular problem? So I have a bunch of terms that depends on xt. I have a bunch of terms that are constant, and then I have a bunch of terms that depends on alpha bar. So what should I erase? Let me erase this side. So I'm going to collect a few terms together. So I have xt transpose q plus plus some constant. So this matrix is positive definite by assumption. What about this matrix B transpose QB? Okay, so the question for you is this a convex function or no? So my claim is that this is a convex function. The reason it is convex is this is a positive definite matrix. This is a positive semi-definite matrix by assumption. So B transpose QB, this is a positive semi-definite matrix. So I add a positive definite matrix and a positive semi-definite matrix, I get a positive definite matrix. So this big matrix you see is actually positive definite. So now I have a UT transpose positive definite matrix UT, and this term is actually linear in UT. So if you can see, this term is basically a constant from the point of view of UT. So this is a linear function of UT, this is a convex function of UT. So overall it's a convex function of UT. One of the things we studied very early on, probably in lecture 6 or 7, is if you want to minimize a convex function, we want to minimize it. See, there is an argmin here that we are looking for. So if I want to minimize this convex function, what do? I take the first derivative, set it equal to 0 and get the value of UT star. So I'll take the first derivative of this particular expression. What I get is 2R plus B transpose QT plus 1B UT star plus 2 alpha bar. There is an alpha bar here as well. B transpose QT plus 1A XT. This is equal to 0. So at the optimal solution UT star, this term, this first derivative must be equal to 0. This 2 alpha bar gets cancelled because it's a constant, and the other side is equal to 0. So what I get is gamma t star of xt is equal to minus UT star and this one is my KT, the control gain at time t. So what we got is the argmin. One other thing that we need to do in dynamic programming is to find out the value function, which is once you find the u star, then you have to substitute this expression of ut star back in this particular expression, and you need to simplify the terms, and what you get is a value function. So this will be your Vt of xt. So Vt of xt, the value function at time t, is basically this expression evaluated at ut star. So I need to put the ut star here, ut star here, ut star here, here and here, here. So once I substitute this expression here, there will be a lot of cancellation, so I am not going to do that thing in the classroom, but I will give you the final expression for what Vt of xt is going to look like, and gamma t of xt, we already know what this looks like. Okay, so let me give you what Vt of xt looks like. Can I erase this side of the board? Okay. This is given by xt transpose. I am going to denote the matrix by st, xt, and the matrix st plus constant. Remember, there is this constant term here. So there will be some constants in the value function as well, but those constants don't depend on any variable of interest. And st is given by A transpose st plus 1a plus q minus alpha bar and st plus 1 equals to qt plus 1. Okay. So let's look at closely what is happening. When the alpha t is always equal to 1, when alpha t is always equal to 1, which means there is no packet drop, then alpha bar is exactly equal to 1 because there is no packet drop, and this alpha bar will be equal to 1. So you get what is known as, so this is known as Riccati equation. So this equation is known as a Riccati equation, this update equation for st. And when alpha t is equal to 1 always, then this alpha bar is equal to 1, and this is the usual Riccati equation. And this is the equation we talked about back in one of the lectures, where we basically get the value function as a function of xt by coming up with this particular matrix st. One thing you will notice is st is always positive semi-definite. So this is always positive semi-definite. And it turns out that this Riccati equation, you can keep propagating the same equation again and again, and you can get the value function as well as the optimal policy as a function of this particular by computing the values of ST at all points of time. So let me write down what the key result here is. Let's write it down here. Oh, I want this expression. So I'm going to substitute, instead of Qt plus 1, I'm going to substitute St plus 1 in these expression. So I get my Kt minus R plus B transpose St plus 1b inverse B transpose St plus 1a. That's my Kt. This is my gain, and this is my value function. And so gamma t of xt is always going to be gain times xt. Now I can erase this side. So what have we done so far? We figured out that, okay, there is a packet drop probability here because of the attack. I need to come up with a control strategy in order to make sure that the system's cost is minimized, the total cost is minimized over a capital T time horizon. Even under the packet drop, I want to make sure that the optimization is done. So what I did was I did a dynamic programming step at the final time step. So I looked at the cost to go at time t. I expanded this expression. I took the expectation, then I minimized with respect to ut by taking the first derivative, setting it equal to 0. And I got that gamma t of xt is actually kt times xt. So kt is the gain that's given by this expression, and that times xt gives me the policy, optimal policy. And in fact, if I compute the value function at that particular point of time by substituting ut star in this expression, I get that xt, the value function is xt transpose a matrix times xt, and the matrix is given by this particular expression. So one thing you will notice is that this A, Q, B, R, these are all the constants of this particular system equation and the cost function. And once I initialize St plus 1 with Qt plus 1, which is my terminal cost matrix, so once I initialize this, I can compute the St, and I get a value function which is of the same format as the value function I had at time capital T. So this was a quadratic function here, and I get a quadratic function here as well. There is a constant, but I want you to ignore the constant because constants do not participate in minimization. When you take the derivative, the constant's derivative is equal to 0. So it doesn't really influence the value of ut. So we are only keeping track of terms that actually influences the value of ut. The important thing to note here is this is a positive semi-definite matrix, this is a positive semi-definite matrix. If you look at this expression, this is a positive semi-definite matrix, but it is entering with a negative sign here. Okay, so So you are actually subtracting a positive semi-definite matrix from another positive semi-definite matrix. But that's okay. It turns out that this particular matrix is still positive semi-definite, despite this being a difference of two positive semi-definite matrices. Anyways, that's great. So I'm able to find the policy, I'm able to find the value function. What you will realize is by running this iteration, so ST will be KT is computed. Let me just write down the expression. So at every point of time, this is what your matrix ST is going to look like, and this is what your matrix KT is going to look like. I've kept it as blank because I don't want to write this whole matrix, but all you have to do is substitute ST plus 1 with S small t plus 1. Okay, that's all you need to do. And that gives you the policy at every point of time. Okay, it gives you a policy for all time steps. That's the main result, by the way, in this paper. This is one of the main results of this particular paper. I mean, it's a survey, but a lot of people have proven results of this type at that point of time. So, wonderful. I want to consider a very specific case. So assume that, suppose this is a scalar suppose this is all scalar, okay? So I'm writing it in a matrix format, but let's assume that all of this is scalar. Let's assume that Q, R, Qt plus 1, all of this is equal to 1. Okay, so everything is simplified. Suppose A is greater than 1. What will happen to ST? Let's say alpha bar is equal to 0. So let me consider the following situation. Q equals to R equals to Qt plus 1 equals to 1. A is greater than 1 and alpha bar equals to 0, which means that I'm preventing any information to pass through from the network. I'm blocking all transmission of information. This was the case in the Jeep Cherokee hack. So this was Jeep hack. All legitimate control signals were completely dropped from the system. There was no possibility of sending the packet once the Jeep was under attack from the hackers. What will happen in this case? Let's look at it. I have xt plus 1 equals axt plus 0 plus wt. Can someone tell me what will happen to xt as time progresses? So x1, so let's say x0 is equal to whatever, x0 is given. So then x1 is equal to ax0 plus w0, x2 equals to a square x0 plus aw0 plus w1, x3 equals to a cube x0 plus something something. So all of this is mean zero random variable, so let's ignore that. What is happening to x1, x2 and x3? So no matter, so if you start with x0, the value of x will grow exponentially fast because you are multiplying a again and again. So you have a raised to t times x naught. So xt a raised to t times x naught. And a is greater than 1. So what happens with xt? Xt blows up. Xt goes to infinity. Okay, so what I mean here is xt goes to infinity because a is greater than 1. Given that the cost function is xt square, what happens to xt square? That also goes to infinity. Okay, so the cost goes to infinity as well as the state goes to infinity. If t is sufficiently large, then these things go to infinity, and we are in a problem. We are in a bit of a problem because we don't want the states to go to infinity. So let me give you a very specific example. Suppose I have a road, and that's a curved road, and there is a car. It looks like a car. So this car is going on this curved road. If you think about the steering, let's say you want to do the steering control. So ut is your steering angle and xt is your distance to the center of the lane. So this is the center of the lane, and if this is the car, then this distance is xt. So if you are driving straight, then of course even if the steering angle is 0, if ut is equal to 0, you are fine. Your xt will always be 0 because you will be going straight on a straight line. So it doesn't matter. But when you are on a curved road, then what happens is your a is greater than 1. So I have not written the system equation, but under these circumstances your a is greater than 1. And what happens when xt is going to infinity? What does it mean for xt to go to infinity on this curved road? It means that your vehicle is not on the road anymore. It's actually outside the road. Okay? So if I am on a curved road, my a is greater than 1, and if my alpha bar is equal to 0, which means that the attacker has hacked in a way that that I am not able to transmit any packet, I am not able to send any information about the control signal to the engine. The steering command doesn't go to the engine, to the actual wheel. What's going to happen? My xt is going to go to infinity, which means I'm going to go away from the road, which is a bad outcome. So what do we want? We want to be able to figure out how to control the system so that it remains on track. Okay, now assuming that alpha bar is greater than 0, in which case by applying this control policy, I can make sure that my xt doesn't go to infinity. Okay, that's the reason why we are studying this particular algorithm. So if you are in this situation, your a is greater than 1, assuming that the attacker has attacked in a way that your packets are getting dropped in an IID fashion with the mean greater than 0, so alpha bar is greater than 0. In this case, by applying this algorithm, by coming up with the Riccati equation and coming up with the kt, the gain value, and applying gamma t of xt, kt xt, by applying this particular gain, I can make sure that my car remains on this particular curved road within the lane markings. Okay, that's the benefit of this particular algorithm. Now, one thing that I want to make sure I mention here is there exists a critical probability alpha bar c such that if alpha is less than alpha bar c, then st goes to infinity. Alpha bar. Oh, I must mention, if rho of A, if the spectral radius of A is greater than 1, then there exists a critical probability alpha bar c such that if alpha bar is less than alpha bar c, then st will go to infinity. What happens when st is going to infinity? If you look at this particular expression, this term goes to infinity and this term goes to infinity, right? And this term is in the denominator, so this is inverse here. So you have this term, this infinity over infinity term that comes here. So basically your control action becomes more and more stringent. So no matter if you get a single possibility of moving the car back onto the center of the lane, you will actually do that if your st is going to infinity. So you want to make sure. So what this basically means, now when is rho a greater than 1? When you are on a curved road. So if your curve is very sharp, your a is rho of a is much larger. If your curve is slight, then your rho of a is sort of, it's greater than 1 but very close to 1. Okay, so given the curve of the road, there exists a critical packet drop probability such that if your packet drop is higher than the critical packet drop probability, then your system will become unstable and you will basically move out of the road. You will go off the road in that particular situation. So this is the practical significance of this framework that we talked about today. Okay. So that's all I wanted to cover for today. We'll pick it up from here in the next class. We'll talk a little bit more about this critical probability part in the next class. And then we'll talk about estimation with packet drops. So right now we have done control with packet drop. So this is control over lossy networks. Next class we will do estimation over lossy networks, which is going to be Wednesday because Monday is a holiday. So we'll do estimation over lossy networks on Wednesday, and then we'll do both control and estimation over lossy networks either on Wednesday or on Friday. So thank you, and I'll see you on Wednesday. Have a great long weekend.